Hello everybody, this is video number 3 about powers in AC voltage circuits. Well, in this video we are going to use this circuit diagram which has been shown over here. This is a series connection of a resistor and an inductor which are connected to an AC voltage, and that combination, that series connection of a resistor and an inductor, is often used in drive technology because that equals the impedance of a motor. So we have a AC voltage which can be described as a sine or a cosine function with an amplitude which has been called EM in this example. Because this is a series connection of a resistor and an inductor, we know that the current will lag the voltage by an angle which is called phi over here, and that angle depends on the values of R and the values of the inductor. But we know that I is equal to an amplitude of the current, Im, times the cosine of omega times t minus that phase minus phi. What we see, of course, is that the frequency of the voltage and the current is the same, but as we said, the current lags the voltage. This can also be shown in a graph and a picture over here, in which the red curve is my voltage, which is the cosine function, and the blue curve is my current, which lags the voltage, because you see that the maximum value of the current is at a later point in time with respect to the voltage. Now we can calculate in this figure the power by multiplying at each point in time the voltage with the current value, and then we get the green curve over here, which has, as expected, when you've seen the earlier videos, which has a double frequency with respect to the voltage and the current. But what we see over here is that the average power is positive. So due to that resistor value, we have a power value of which the average value is positive. Well, let's see if we can also calculate that average power. We expressed the voltage over here, we expressed the current over here. Now let's calculate the instantaneous power, P as a function of t, by multiplying the voltage and the current, and then we get P is E times t, which is equal to the amplitude of the voltage times the amplitude of the current, which stands over here, times cosine omega times t, times the cosine of omega times t minus the angle phi, which equals Em times Im divided by 2 times the cosine of 2 times omega times t minus phi plus the cosine of phi. And why was that? Because we use this Gonia formula, which says that the cosine of alpha times the cosine of beta equals half the cosine of the summation of both arguments plus half times the cosine of the subtraction of both arguments. So then we get the double frequency over here, which we have seen over here, plus we have a term over here, which is the subtraction of this argument of the sine and the argument of the cosine. So we can express this again as the RMS voltage, which is equal to Em over the square root of 2 multiplied with the RMS value of the current, which equals Im over the square root of 2. And then we can calculate the average power, which is the average value of this complete expression. Well, we have seen that when we have a cosine with a time function in it, so it's what we call a running cosine, that the average value, of course, is 0. So then we get that the average power P is equal to the square P, which equals Em times Im over 2, which equal to the RMS value of the voltage times the RMS value of the current, times the cosine of phi, which is the phase shift of the current with respect to the voltage. So my average power, which has the unit watt, equals the RMS voltage times the RMS current times the cosine of the phase shift between voltage and current, cosine of phi. Well, when we have this, we can call P, the active power, as I said, in watt, and cosine of V is called the power factor. The combination of E times I is called the apparent power, and it has the unit V times A, voltage times ampere, also called volts times amps. So it's a different unit with respect to the unit of P, which is in watts. So by seeing this unit, you can immediately see that this is applicable to the apparent power S. So S equals E times I. Now let's replace that series connection of R and L by a parallel combination, a parallel connection of R and L connected to that AC voltage source. And let's call the current through the resistor IP, and let's call the current through the inductor IQ, and the summation of both currents is called the current I. Now we can draw the phasor diagram, and we do that by putting the voltage E, the amplitude of the voltage over here, on the horizontal axis. We know that the current through the resistor is in phase with the voltage over here, the source voltage. So the current IP, the vector of that current, is on the same axis, so the horizontal axis, as the voltage, because as I said, both the voltage and the current, the voltage over resistor, current through the resistor, are in phase. The current IQ, the current through the inductor, lags the voltage by 90 degrees. This is minus 90 degrees, or minus p over 2 radians. So the vector IQ is on the minus negative axis. And the combination of IP and IQ, the summation, is the summation of the vector IP and the vector IQ, and that yields the vector I, which is the current over here. And that current I makes an angle to the real axis, which is equal to that angle phi, as we defined before. So now we can say, well, IP is I times the cosine of phi. Why is that? Because the cosine of phi is IP divided by I. And we call that the active current, the current through the ohmic part of my impedance, so through that resistor. IQ is I times the sine of phi. IQ is over here, so it's also over here, and we can see that the sine of phi is equal to IQ over I. And IQ is called the reactive current. I is called the apparent current, and that is the vector summation of IP and IQ. And of course, what you can see is you can calculate it by taking the square root of IP squared plus IQ squared. So IP is the active current, IQ is the reactive current, and I is the apparent current. And that apparent current is always higher than the active current. Now we can also define the different power parts. We have seen that P, the active power, was equal to E times I times the cosine of phi, the cosine of that angle, that phase shift between voltage and current. So P, the active power, is E times I times the cosine of phi, which is equal to E times IP. Remember, IP was I times the cosine of phi. Q, the reactive power, is E times I times the sine of phi. So that equals E times IQ. And the reactive power has its own unit, and that is VAR, which stands for volt ampere reactive, volt amps reactive. We have seen P has the unit watt, Q has the unit volt amps reactive, and S has the unit volt times amps. So summarized, we have three types of power in an AC system with complex impedances. We have the apparent power S, which equals E times I, which has unit V times A, volt amps. We have the active power, which is P, which equals E times I times the cosine of V, and it has the unit watt. And we have the reactive power, which is Q, which is E times I times the sine of V, which has the unit volt times amps reactive. We can also see that we can calculate S by taking the square root of P squared and Q squared. Well, that's all about power and AC systems, and in this situation with a complex impedance. Thank you for watching.